In the second part of our study of substitution of alpha to carbonyl groups, we are going to examine aldol condensation and related reactions. First, we are going to look at aldol reaction. Aldol means aldehyde alcohol, so aldehyde alcohol, aldol. Aldol reaction is a very important reaction because it's one of the reactions for formation of carbon-carbon bonds. Aldol reaction is based on the fact that enolate anion is a nucleophile. So deprotonated carbon alpha to carbonyl group is a nucleophile. At the same time, carbonyl carbon is an electrophile. So if in the mixture we have partially deprotonated carbonyl compound, we'll have mixture of deprotonated carbonyl compound and protonated carbonyl compound. So mixture of nucleophile and electrophile. Reaction of the two species, nucleophile-electrophile reaction, will result in formation of new carbon-carbon bond, because here we have carbon nucleophile and carbon electrophile. Of course, carbon electrophile is carbonyl carbon. Specifically, aldol reaction is reaction of two molecules of aldehyde. And of course, two molecules have to be identical. So, two molecules of aldehyde react to form an aldol. Here we have example of two molecules of acetaldehyde. Reaction is reversible, and in case of aldehydes, equilibrium is to the right, to the product, towards the products or aldols. Reaction also could be carried out with ketones, but under conditions of aldol reaction, it is not favorable. Equilibrium is actually to the left, towards the ketones. So in this case, we have to carry out reaction under a little bit different conditions, which we will examine next under aldol condensation. Reaction mechanism involves deprotonation of an aldehyde, acetaldehyde in this case, and deprotonation with base such as hydroxide or alkoxide results in deprotonation of only about maybe 1% or less or fewer molecules of the aldehyde. So 99% of them are still in protonated form. So those deprotonated molecules of the aldehyde add to protonated form, to those that were not deprotonated, to form new carbon-carbon bond. Of course, according to Le Chatelier's principle, as soon as some of the deprotonated molecules react, they are removed from the equilibrium, and so more of the molecules of aldehyde are deprotonated, and this process keeps continuing until all of the molecules of aldehyde are used up in this reaction. Once addition occurs, so next step is addition of nucleophilic addition to carbonyl carbon of the aldehyde. Once addition occurs, alkoxide forms, and that alkoxide is protonated. In aqueous solution, it's protonated by molecule of water. In solution of an alcohol, it will be protonated by molecule of an alcohol. That regenerates base catalyst, which means that this reaction is base catalyst. We only need a small amount of base as a catalyst. And reaction product is the corresponding aldol. All of the steps are reversible. In case of ketone, steps are the same. Ketone is deprotonated, in this case acetone, and then deprotonated ketone adds to carbonyl carbon of another protonated molecule of the ketone. In this case, product would be ketal, which is protonated, or alkoxide of the ketal, and it's protonated to ketal. It is just that in this case, equilibrium is unfavorable, and equilibrium is to the starting materials. So this reaction, as shown here, will not work very well. With aldehydes, it works very well, but not with ketones. But we can carry out reaction under alternative conditions, as condensation. In organic chemistry, term condensation is rather old, and it refers to organic reactions. It means reaction that occurs with evolution of a small inorganic molecule. Typically, that molecule is water. Typically, under condensation conditions, this molecule of water boils off and condenses, and that's why it was called condensation reaction. Other small molecule could be involved, like molecule of ammonia or molecule of alcohol. The only difference is that under condensation conditions, reaction is carried out with heating. So we first carry out aldol reaction, as usual, but if we carry out reaction with heating, then elimination occurs, elimination of molecule of water, and we end up with alpha-beta unsaturated aldehyde. So condensation results in elimination of molecule of water to produce alpha-beta unsaturated aldehyde. Reaction can occur under acidic conditions, as shown in this case, or it can also occur under basic conditions. And this reaction with ketones is actually favorable. So if we carry out only aldol reaction with ketones, that's unfavorable reaction. But if we carry out reaction with heating, then elimination of water occurs, and that's favorable reaction, and alpha-beta unsaturated ketone is the final product. So while aldol reaction with ketones was not favorable, equilibrium was not favorable, aldol condensation is favorable and proceeds readily. So that's the only difference, heating. And note that in this case, elimination of water occurs under basic conditions. That's one of the few reactions where elimination of water can occur under basic conditions. That's typically not favorable, but under conditions of aldol condensation, it is a favorable reaction. Finally, if a 5-membered ring is involved, as in 5-membered ketone, cyclopentanone, then elimination of water or aldol condensation is a spontaneous reaction. We don't need heating. The reason for this is that in 5-membered ring, introduction of a double bond eliminates torsional strain. We covered that earlier in Organic 1. 5-membered ring is known for torsional strain and for not being able to avoid torsional strain. Introduction of double bond removes some of the hydrogens responsible for torsional strain, and for that reason, introduction of double bond in a 5-membered ring is very favorable reaction. So when 5-membered ring is involved, you should remember that we cannot stop at aldol reaction. Reaction proceeds all the way to condensation. Now here is the mechanism of elimination of water under basic conditions, since this is somewhat unusual reaction. Under basic conditions, first aldol, or in this case highlighted in yellow is ketol, forms. Under basic conditions, it undergoes alpha deprotonation. So deprotonation alpha to carbonyl to give enolate anion, and now this enolate anion undergoes intramolecular reaction to eliminate hydroxide anion. So electron pair on alpha carbon forms carbon-carbon pi bond, and that's accompanied by breaking of carbon-oxygen bond, and that results in formation of alpha-beta unsaturated ketone. So molecule of water is eliminated first in deprotonation step as H+, and then in loss of hydroxide OH-. Now, we can also attempt crossed or mixed aldol reaction. Typically, aldol reaction is carried out on one compound, where a single compound is both source of a nucleophile, that means enolate anion, and electrophile, reacts in protonated form. But we can attempt crossed or mixed aldol reaction. If we simply mix two molecules of an aldehyde and add a base, that reaction is not preparatively useful, because we get all the possibilities. So one aldehyde is deprotonated, or the other aldehyde is deprotonated. In this case, we have ethanol and propanol. And so we have all the possible combinations. For example, anion from propanol reacts with ethanol to give corresponding aldol reaction product. Or we can have an ion of propanol reacting with another molecule of propanol to give corresponding product. Or an ion of ethanol reacting with another molecule of ethanol to give the product, or an ion of ethanol reacting with molecule of propanol to give corresponding product. So we'll get 4 possible products. We may not get them in equal amounts, not 25% each, but we will get them in some approximately 25% similar amounts. So this is reaction that gives very bad mixture, and it's not preparatively useful reaction. So as a general rule, crossed or mixed aldol reaction is not preparatively useful reaction. But it could be made into preparatively useful reaction if first we start with a ketone and deprotonate ketone and use non-enolizable aldehyde. Non-enolizable aldehyde is aldehyde that does not have alpha protons. Typical such aldehydes are aromatic aldehydes. Then only ketone will be deprotonated and will result in formation of enolate anion. Now that enolate anion could conceivably react with another molecule of ketone, that means in this case another molecule of acetone, or it could react with benzaldehyde. Recall from previous chapters that aldehydes are much more reactive than ketones because they exhibit much less steric hindrance. So for that reason, only ketone can produce inlet anion and can only react with aldehyde because the aldehydes are much more reactive. So we have only one type of reaction, only one reaction can occur, that of inlet anion from ketone with an aldehyde. And we end up first with, so this is the aldehyde, benzaldehyde. First we end up with aldol reaction, and in this case, because we have aromatic ring and carbonyl group, elimination of water is spontaneous reaction, because resulting double bond is conjugated both with aromatic ring and with carbonyl group. So there is extensive electron delocalization. If stoichiometry ketone to aldehyde is 1:1, reaction will stop here. Or alternatively, we can carry out reaction with stoichiometry of 1:2, one equivalent of ketone with two equivalents of aldehyde. Then one more reaction will occur on the other side, on the other alpha carbon of the ketone, and we end up with this final product, with di-substitute product. So result of two aldol condensations of a ketone. So in conclusion, mixed aldol reaction, mixed also means or crossed, aldol reaction works, but it works only if we carry out reaction between ketone and an aldehyde, and aldehyde is non-analyzable aldehyde, such as aromatic aldehyde. With dicarbonyl compounds, aldol condensation could be carried out as intramolecular reaction to form rings, to form ring compounds. So here we have an example of 2,5-cyclohexadione diketone. A reaction with hydroxide, like sodium hydroxide, results in formation of two possible inlet anions. So inlet anion from 2,5-cyclohexadione could be on carbon 1 or on carbon 3. So let's look first at carbon 1. Inlet anion from carbon 1 will react with other carbonyl group on carbon 5 to close the ring. And the ring that is closed is 5-membered ring. You can simply count carbon atoms and convince yourself that it's 5-membered ring. Alternatively, inlet anion could form on carbon 3. That one will result in formation of 3-membered ring. As you may recall, these reactions are equilibrium reactions. They are reversible reactions. 3-membered ring, as you know from organic 1, is extremely unstable. It has very high angle strain and very high torsional strain. So under these conditions, 3-membered ring will reopen to reform starting inlet anion. And so inlet anion in position 3 will not result in further reaction. Instead, it will equilibrate, so it will be protonated back to dicarbonyl compound, to 2,5-cyclohexadione, and then deprotonated again until it gives carbanion in position 1, inlet anion in position 1, and that one will form 5-membered ring. So the only ring that results eventually in a reaction is 5-membered ring, and that ring is protonated to first result in aldol reaction, and as we just covered, 5-membered rings spontaneously undergo elimination of water to give aldol condensation products. So in this case, aldol condensation product, 5-membered ring, alpha-beta unsaturated ketone is the reaction product. From this you can draw a conclusion that when there is competition in intramolecular aldol condensation between formation of 3-membered ring and 5-membered ring, 5-membered ring will form. Now in the next example, we have 2,7-heptadione. Now competition is between formation of 5-membered ring and 7-membered ring. So again, anion upon treatment with hydroxide could form in position 1 and 3. Now formation of inlet anion in position 3 results in cyclization to 5-membered ring, while anion in position 1 cyclizes to form 7-membered ring. So this will be 5-membered ring, position 3, 7-membered ring, position 1. We did not cover that earlier in the course, but medium-sized rings, 7, 8, 9, do exhibit strain, more strain than 5 or 6 membered rings. For that reason, 7 membered ring will reopen. Also, there is another factor, and that's called entropy factor. Odds of 7 membered ring forming are much lower compared to 5 membered ring. That's because carbon atoms needed to form 5 membered ring are closer to each other. And because of the thermal motion, chain freely flips around and rotates, and 5 membered ring is much more likely to form compared to 7 membered ring. Simply, there are many more degrees of freedom when it comes to formation of 7 membered ring. For that reason, formation of 5 membered ring is preferred, and that's the only product. Again, as before, aldol reaction is initial reaction product, and since this is 5 membered ring, aldol condensation is spontaneous reaction. Elimination of water is spontaneous reaction. So when there is competition between 5 and 7 membered ring, only 5 membered ring forms. And the same is consideration when there is competition between 4 or 6 membered ring or 6 or 8. Note that in intermolecular aldol condensation, rings that can close always differ by 2 carbon atoms. So competition is 3 versus 5 or 5 versus 7, or 4 versus 6 or 6 versus 8. In all of those cases, only 5 and 6 membered rings form. 3, 4, 7 or 8 membered rings do not form simply because they have either higher strain, or which means they are less stable, or odds of those rings closing are much lower compared to closing of 5 or 6 membered ring. When there is a reaction, intermolecular reaction of compound that is both ketone and an aldehyde, that means oxoaldehyde. In this case, it would be 4-oxopentanal. Then inlet anion forms on a ketone, and again, 5 membered ring forms preferentially to 3 membered ring. Alternative ring here that could close would be 3 membered ring, and again, since it's 5 membered ring, initial aldol reaction product undergoes water elimination to give aldol condensation product. Another type of condensation reaction is that of esters, and that's called Claisen condensation. So in a Claisen condensation, a molecule of an ester undergoes condensation. So it's 2 molecules of an ester that react with each other. One is deprotonated and acts as a nucleophile, and reacts with one that is not deprotonated and acts as electrophile. When it comes to esters, we have one very important limitation. We cannot use, for example, hydroxide, because that one would hydrolyze the ester. That would be base-induced hydrolysis of an ester. The base that we used is limited to leaving group of the ester. So in this particular case, we are dealing with ethyl acetate. So leaving group is, since this is ethyl ester, leaving group is ethoxy group. That means that we must use ethoxy base, such as sodium ethoxide or potassium ethoxide. The best solvent for particular ethoxide is corresponding alcohol. So, or for particular alkoxide. So for methoxide, best solvent is methanol. For ethoxide, ethanol. Isopropoxide, isopropanol, and so on. So in this case, we will use ethoxide, since that matches the leaving group of the ester, and solvent will be ethanol. You will see in a minute, in this case, additional step, protonation step, is required. Reaction products are beta ketoesters, and that's because esters have a leaving group. So leaving group lives in the course of this reaction. Here is the reaction mechanism. So ethoxide as a base deprotonates ester in alpha position. Of course, only a few molecules of ester are deprotonated. Most of them are not deprotonated. So in the next step, those few deprotonated molecules react as nucleophiles. So alpha carbon adds to carbonyl carbon of another molecule of the ester to give the addition product. Addition is to carbonyl carbon. And of course, according to Lesch-Tolier's principle, as soon as those deprotonated molecules are used up, more molecules of ester are deprotonated, and reaction continues until all of the ester is used up. This addition product, tetrahedral intermediate, now reforms carbon-oxygen double bond. and at the same time, simultaneously, leaving group, ethoxy group leaves. That regenerates a base catalyst. But as you will see in a minute, reaction is not catalytic with respect to base. Upon loss of the leaving group, in this case ethoxy group or alkoxy group in general, product is beta ketoester. And you can see that here. So beta ketoester is the product. Now, reaction should stop here, or one would expect reaction to stop here, and one would expect it then to be catalytic with respect to base. But that's not the case, because resulting beta ketoester is highly acidic. It has alpha carbon that is activated by two carbonyl groups. So that alpha carbon is deprotonated by base that is present in the solution, and this deprotonation is quantitative because this alpha carbon is rather acidic. So all of the ethoxide is used up in 1-to-1 ratio, one equivalent of beta ketoester with one equivalent of ethoxide react to give this corresponding inlet anion. And so for that reason, first we need stoichiometric amount of base, and secondly we need this second protonation step. So this inlet anion has to be protonated so that we can finally isolate beta ketoester as the reaction product. If necessary, we can also carry out crossed or mixed Claisen condensation. But to do that, of course, again, as in case of aldol condensation, crossed or mixed aldol condensation, we cannot simply mix two different esters and just add base. First, when we mix two esters, they have to have leaving groups that match. So both esters have to be, for example, methyl esters or ethyl esters or isopropyl esters. So those two leaving groups have to match. Secondly, one of the esters must be non-enolizable, so aromatic esters, like in this case, ethyl ester of benzoic acid, so ethyl benzoate, so that only one ester is enolizable. And then finally, that ester that is non-enolizable should be used in large excess, so that inlet anion is formed from the enolizable ester. Odds are that that inlet anion will react mostly with non-enolizable other ester. Of course, the base must match the leaving groups of the two esters. Since this is ethyl, then base must be ethoxide in ethanol, and of course, as usual, we have acidic workup, and then product is beta ketoester. Beta keto group comes from non-enolizable ester. There are numerous variations on this crossed or mixed Claisen condensation, and they don't necessarily involve two different esters. They simply involve two different carbonyl compounds. And here are some examples. For example, ketones are much more acidic than esters. So if we carry out mixed reaction on ketone and ester, it is ketone that will be deprotonated. And then addition to ester that is used in excess results in formation of diketone, beta diketone. That's because ester has a leaving group. If we use simplest ester, ester of formic acid, then the substituent on ester carbonyl is hydrogen instead of alkyl group, and then product is beta ketoaldehyde. We can also use carbonate as ester. Carbonates are esters of carbonic acid, so they have two alkoxy groups on carbonyl group. And then product is beta ketoester. And finally, here we have an example of diester of oxalic acid, so diethyl oxalate, and reaction with ketone. So ketone is deprotonated, being much more acidic, and actually oxalate doesn't have any alpha hydrogens, and then reaction with diethyl oxalate results in this rather interesting tricarbonyl compound. So this is diketoester. Claisen condensation can be carried out as intramolecular reaction if compound is diester. Intramolecular Claisen condensation is called Dieckmann condensation. And in this case, only one product is possible. When trying to determine product of intramolecular Claisen condensation, of Dieckmann condensation, it's a good idea to redraw the chain of the diester. And you redraw it in such a way that alpha carbon is close to the other carbonyl group. So alpha carbon of one carbonyl group is close to the other carbonyl group. And then you can draw a bond that forms. It's shown here as dashed line. So bond is going to form between alpha carbon and carbonyl carbon. And also leaving group on that carbonyl carbon to which bond is going to form, leaving group is going to leave. That's going to be alkoxy group. And then it's very easy to determine what is the reaction product. You simply remove the leaving group and newly formed bond is there, and that's the product. In this case, 5-membered ring. In this second example, we repeat the same process, redraw the chain in such a way that alpha carbon of one carbonyl group is close to carbonyl carbon of the other. We draw the bond, in this case as dashed line, that is going to form, determine what is the leaving group, that group will be gone, and we can see that now product is 6-membered ring. Mechanism of Dieckmann condensation simply involves deprotonation of one of the alpha carbons. Again, base must match the leaving group. So we are using in all of these cases ethoxy leaving group and ethoxide as a base. So deprotonation results in formation of anion. That anion adds to carbonyl carbon of the other leaving group, of the other carbonyl group. That results in formation of tetrahedral intermediate. Tetrahedral intermediate reforms carbon-oxygen double bond, and that's accompanied by leaving of the leaving group, ethoxy group, and that results in formation of the final product, and that's cyclic beta-keto ester. This completes the second part of the chapter on alpha substitutions of carbonyl compounds, and next we are going to examine 1,2 and 1,4 additions to unsaturated carbonyl compounds.